Okay, afternoon everyone. So let me just recap what we were doing last lecture. So we were talking about measurements, and so one of the key aspects of quantum wave functions is that they're normalized, right? So each state of the wave function, if you check the overlap with itself, it's equal to 1. And if you have the coefficients, then the modulus squared adds to 1. And the reason why we kind of assume that, or we impose that on a quantum wave function, is that basically these have the interpretation of probabilities. So if you were to measure the state of a particular wave function, so I should really have that wave function written there. What I have in mind there is something like this. And, oh yeah, sorry, keyboard duties. Then if you're measuring in this basis n, then it probably doesn't matter for this one. Yeah, I'm not going to write that much more. So if we're measuring in this the state n, and then the probabilities of that come out with the modulus squared. So just as an example, these n's that we talked about, these are the kind of the basis vectors. These are actually associated with specific physical states of the system. So for example, in this example here, maybe the electron goes left or right. If it goes left, we'll call that state 0. If it goes right, it's state 1. And these are completely random. And it's not random because there's some kind of noise in the system. It's because quantum mechanics has this randomness that you can't really get rid of, actually. And so in practice, what that means is that in an experiment, you might run it many, many times to figure out what these probabilities are, just like rolling a die, many times to figure out what the probabilities in a quantum experiment like this, you do the same thing, same experiment 1,000 times, for example, and then you work out probabilities from that. And so for a qubit, this is our simplest quantum system. For example, we might do measurement 0 and 1, and then the probabilities will come out like this. And what you notice here is that the state actually changes during that measurement. And so this is another feature of quantum systems that you can't, generally speaking, you can't measure the system without disturbing it. By measuring it, you sort of change the system. This is, there's different kind of analogies for this, but it's a bit like how, if you look at something, then somehow that changes it forever. So this thing where the state changes is called wave function collapse. But after you've actually measured it, the state actually changes, and then if you measure it again, then you'll always get that state. So, a way of thinking of this is that you've measured it, then it becomes kind of a classical state, just because, classically, we are able to always tell the difference between 0 and 1. We've introduced a bit of mathematics to handle this process, and we do that with measurement operators. Measurement operators, in this case, are projection operators like this. Actually, more generally, the measurement operators can be doesn't have to be projection operators, but for whatever we'll do in this course, we'll just use projection operators, the simplest example. And basically how this works is that when the measurement happens, you apply the measurement operator, and that's basically what the state is after the measurement. But you need to normalize the state because the state after you measure it actually is often unnormalized. So this is just, so basically it's m times the state. That basically gives you what the state after the measurement is. But basically you got to renormalize it because it might not have a norm of 1. So this is what that factor is. And the probability turns out to be equal to this. It's basically the length of the vector, which is m times psi. This is basically norm squared of m psi. Some examples like this. You can also use matrix notation. And we confirm this kind of relation where if you do a measurement and then you do a measurement again, then you'll get with 100% probability the state that you just got. So if you got 0 on the first time, then if you go and measure it again, you're going to get 0 again, and you'll get that with 100% probability. And finally, I think the last thing we did was this global phase business. So the global phase is basically just a phase factor, so that each of the I factor that multiplies any wave function. So this is just one example of global phase. More generally, it's just like, anything like if I just multiply this by e to the I theta, that's what you call a global phase. It's just e to the I phi theta, just multiplying the whole wave function. And such phases basically you can't see them even if they're actually there. It's because basically all the formulas for the probability are things like the, for example, that, product with itself. That's the probability of getting 0. And basically all these phases always kind of cancel out, or you can just never see these phases. So you can have them, there's nothing wrong with having them there, but it just doesn't change any of your answers. So actually these are all physically equivalent states. Actually. So there's no real difference in the physics or any observables of any of these. Okay, so let's just do this question as a refresher. So I have a qubit that's in the state this. So we had a similar example before. I feel like we did this first one. Yeah, okay, so the difference is that previously we just looked at the coefficients and then did modulus squared, and then you said it was like 3/4. Okay. Everything was fine. So yeah, previously you just took the modulus square of this thing, right? And then you said 3/4 probability here and 1/4 probability here. So basically the difference now is just let's use measurement operators to work out the same thing. So you'll need a bit of pen and paper to do this. But just let's confirm that we get the same result. I'll put up the key formulas. So measurement operators in this case would be like this. And then the measured state after measurement will be this. And that. So I'll just give you a couple of minutes just to do that. see you're working. Just erase it. Oh, okay. Um, Yeah, so I think most of you are getting there. So basically, first step to these things is always to evaluate this quantity here, because from this quantity you can get like this quantity later. So so m0 psi is 0, 0, so it's definition, and in this case we've got root 3I on 2, 0 plus half 1. And then just expand this out, you're going to get 3I on 2, 0, 0 plus a half of 0, 1. This thing is 0, this thing is 1. And then so you get 3I over 2, 0. And then to work out the probability, it's basically just the norm of this thing, right? It's the norm of this. So basically, we just have to find the overlap of this with itself. So E0 is going to be psi of M0 dagger 0 that. This thing is just the complex conjugate transpose of that. So this is minus 3I over 2 at bra of 0. And then this one is 3I over 2 0. This thing times this thing. And then these constants, you just multiply. Any factors of I always disappears because it's I times minus I. So this is 3/4. 0 over 0. This thing's 1 3/4. And to get the measured state, well, the 0 outcome, measured state. So it's this thing that we just calculated here divided by square root of probability. So 3 over 2I of 2, 0 divided by 3 over 4. Probability that we just calculated. Basically, always these numbers here are designed to cancel out. I mean, this thing, it has to be a normalized vector. So, obviously any numbers here have to kind of all cancel out. If there's some number here, then it means it's not normalized. So 3 cancels, 2 But because I is just a phase, that can actually be there. Right? So, well, if you just follow the formula exactly, this actually would be I times 0. But this is this global phase that never does anything that we'd be talking about. So, okay, strictly speaking, this is the answer, but physically speaking, it's kind of equivalent to just 0 because it will never change anything. But, okay, mathematically, I mean, actually, it's I times 0 step. Yes. Yeah, so that is exactly this, what happened here. So in this example, remember, so this number here is alpha, right? In the notation. So this is alpha, and this thing is kind of mod alpha. Yeah, so to match the notes here, it's root 3I over 2. And, well, another way to write this is like this, right? Yeah. And then mod alpha is just the radius in the whole of notation. this is just root 3 over 2. Yeah. So this thing is just always kind of left over when you do this division. But as I said, it doesn't really affect things. It doesn't actually matter so much. It's not really important because it's a global phase. And often in physics, you might even just drop it because everybody knows it doesn't do anything. But if you wanted to really just be exact to the formula, the answer would be I times 0 star. Okay, all right, so I think we're done for that slide set. Any questions for this measurement stuff? Looks like no. So let's move on to the next one, which is basis rotations. So, well, okay, let me just already start with this without any introduction. So, so we're familiar with, well, if you're familiar with vectors, then you're probably familiar with coordinate systems. So let's just forget about quantum mechanics and just think of a slightly conceptually simpler example. And let's just think about another vector of velocity. Okay. So suppose we've got two people and they're looking at some plane in the sky. Plane is moving in the sky. Now, often in quantum information, we call the two people Alice and Bob for historical reasons. Not named after anybody. Main things that they start with A and B. So, we'll start introduce these two people, Alice and Bob, and so Alice is looking at the plane. It's sort of flying over her head this way. For Bob, he's facing the other way. It's going this way. Right? Okay, so obviously, because they're not facing the same direction, they will measure the velocity to be different, right? Because Alice's coordinate frame, the velocity is sort of going backwards, right, relative to her. And for Bob, it's going forwards, right? So the plane is physically obviously going in the same direction. So there is a kind of element of reality to the velocity vector, right? So it's not that just the velocity of the plane is somehow arbitrary and changes according to whatever you sort of whatever you think. There's a kind of a reality to it, and in fact, the arbitrariness is due to the arbitrariness of the coordinate system that you can choose. So you can choose an infinite number of coordinate systems to describe the same vector. So in a sense, the real thing is kind of this thing. There's a real velocity, and it's really going somewhere, but then how you describe it is somewhat arbitrary. So Alice's coordinates might be like the black ones, and the Bob's might be totally different. So same thing happens with quantum mechanics. So we've been saying that here is the quantum state. And we've been saying that, okay, well, this quantum state is described by some superposition of vectors. These are kind of our basis vectors. And they have some coefficients. Okay. Now, actually, the choice of these basis states is actually kind of arbitrary. We could have actually chosen a bunch of different coordinate vectors, and we could have described the state in kind of a different way. And so for example, perhaps you choose a different coordinate system, maybe these ones labeled by B. So these were a kind of different unit vectors. And obviously they would have different coefficients, right? Because just like our Bob, in Bob's coordinates, the vectors looks, the coordinates in Bob's coordinates are totally different to Alice's, right? But it's still the same thing that they're looking at. So these coordinates that Bob's basis, Bob's coordinates, these numbers are entirely different to whatever these numbers are. But yet they're still the same state, because the state has a kind of a reality to it. The state is really in this particular state, and what's happening is that there's a kind of a freedom of coordinates to actually describe that. But that probably makes total sense in terms of mathematics. But remember that But remember that these vectors were actually some kind of physical state, right? Remember, we were giving various examples of different states. Previously we were saying stuff like, okay, well, these states might be like levels of an atom, or maybe there's some channel that an electron goes left or right. If it goes left, it's 0. If it goes right, it's 1, so forth, right? We started off by saying that, well, these are going to be our basis vectors, like this or this. But what we're basically now saying is that actually, well, we didn't have to choose those basis vectors. That's just actually one example of kind of basis vector set that was kind of conceptually easy to understand, right? But there are actually other choices of basis vectors that we could actually describe the state in. So we'll maybe show a couple of examples soon. But let's do let's start with the simplest possible example of this. So let's again look at a qubit. And let's start with our kind of general state like this. Alpha and beta on these states 0 and 1. So again, physically it might be like this, or the 2 lowest level of an atom or something. Now, we can actually represent this state using some other vectors like this. And there's sort of an infinite number of such vectors that you could use, but a common one that we're going to encounter a lot are these so-called plus and minus states. And these plus and minus states are defined like this, and these states are basically like equal superpositions of the 0 and 1. And plus is plus, and then the minus is the minus between. Okay? And these states are actually, obey exactly the same kind of properties that our original basis states, like 0 and 1, do. So, for example, they're orthogonal. So, if you take the inner product between plus and minus, then what you find is, so just substitute this, for plus, take the transpose of this thing, then you're going to get 0 plus 1 here, that's the plus 1, and 0 minus 1, that's that minus. And then when you calculate this. So 0 overlap with 0 gives 1. 0 overlap with 1 just is 0. 1, 0, 0, and 1, 1. It's 1. So the only two terms that are non-zero are 0 and 0 and 1 and 1. But then there's a minus sign here, right? So it's inside, when you expand this, it's going to be 1 minus 1, and it's going to be 0. Right? So these are orthogonal. And just like the original 0 and 1 vectors, they have a norm of 1. Right? Length is 1. So if you find the length of plus and plus, then this you'll find is well, you do the similar kind of calculation here. Inside the bracket, you're going to get like 1 plus 1. 1 plus 1 is 2, and so this will be 1. So they're orthogonal, they're normalized, and we can actually kind of visualize it as being some kind of like thing that's like 45 degrees to the original axis. Yeah, so actually we sort of skipped ahead maybe a couple of lectures ago and actually already did something like this, but don't hurt to do it again. So how do you write it in the new coordinate system? So if you wanted to write this state in this new basis, how would you do it? So firstly, you need to invert the relation that you give. So instead of having plus in terms of zeros and ones, what we would like is a relation that gives like 0 and 1 in terms of plus and minus. So by adding these two equations, so if you add equation 1 to equation 2, then you can get the ones to cancel on the right-hand side. And then what you'll find is that 0 can be written this way. To get 1, you basically subtract equation 1 from equation 2. Then you'll get zeros to cancel. And then you'll have this relation here. Then if you can just substitute that into the original form of psi, then this is the 0 state, this is the 1 state, and then we can now factorize it. So we've got pluses, so there's a plus sign between them, so it's alpha plus beta. And then for this one, there's a minus sign between it because of this minus sign here. So the plus, so the minus, the alpha minus beta, and voila, we've rewritten the state in terms of the plus and minus basis. So basically, in this new basis, this state has different coordinates. Obviously, this number here, alpha plus beta over root 2, or alpha minus beta over root 2. These are different numbers to this one, right? So new coordinate system, new numbers, and that's the coefficients that we find. Okay. So you might wonder, okay, mathematically fine, but what does it really sort of mean in terms of the physical system, right? Because so if we are, kind of rewriting our state in terms of the plus and minus, what is this plus or minus state? Well, basically the plus or minus state is the state that's in a kind of a superposition of say left and right channels, right? So this plus state, as you can sort of see from definition, is essentially this state that's both in the left and the right channel at the same time. And in a superposition, there's always some kind of phase, and so it kind of has a plus phase between them. The minus state obviously has a minus phase, but again, that's also a state where it's both in the left and the right channel. The plus state in terms of the atom would basically mean that the electron around the atom, nucleus here, is simultaneously in the lowest energy state, also the first excited state. So, it's a bit of a peculiar example, physically speaking, but basically there's nothing to stop you from rewriting it in terms of this basis. The basis elements itself actually create, has some kind of quantum effects sort of inside it already, if you like. But that's completely allowed and equally valid way to represent any state. Okay. All right. So that plus and minus is just one example of a different basis that you could choose. As I said, there's a sort of an infinity of these different bases. So for qubit, we can actually write down the most general pairs of coordinates that you can have. So let's say this A is like the original basis, maybe like physically, either definitely left or right, this type of thing. And let's try to construct a more general set of bases using the A's, the original bases. So essentially the job is that you want to write down a pair of vectors which are orthogonal. So if you take the inner product, then they'll give you always gives you 0, and also they should be normalized too. So we can do that pretty simply for a qubit system. And for say we have maybe I shouldn't have used alpha and beta because this is like the previous slide, that was the state. But what I mean by alpha and beta here are just arbitrary parameters. Okay, two complex numbers, but then they would be normalized. And so maybe for the first vector, we can choose this 0 state to be just this alpha beta. And then in order to make sure that this second one is orthogonal to it, we should choose the parameters like this. And it's basically like the complex conjugate. You swap the coefficients, complex conjugate, and then minus. In general, it's not obvious to figure out what's the orthogonal version of the vector, but in this case, it's a two-dimensional example, and it's simple enough. If you did this for the first time, then this would not be an obvious thing, but this is a common enough example that it's pretty well-known formula. So we can tell that these things are they're both normalized and orthogonal, and so for 0, 0, I mean, we kind of started with this definition. So if you take the overlap of inner product of 0 with itself, then again, only these terms with 0, 0 and the 1, 1 survive. And so this is alpha mod squared plus beta mod squared, which is 1. If you take the inner product between 1 and 0, then you can tell that these are always orthogonal and this is why you need the complex conjugate on the 1 here, because when you turn this into the bra version, you need to take a complex conjugate of all these coefficients, right? And then so this ones with the stars become no stars, right? And then when you take the inner product of that with this one, then you're going to get these two terms, so that term was going to give beta alpha, and then these two terms, this is going to give alpha beta. Beta alpha and alpha beta are the same, so this is going to be 0. So these are always orthogonal vectors. And for 1, 1, did I do 1? No. Simple enough. 1, 1, you can see that this is normalized, because if you did the bra of version of 1 is beta 0 minus alpha 1, and 1 is beta star 0 minus alpha star 1. Again, only these two terms are non-zero in the expansion, so this will be beta squared and alpha squared. These two minus signs cancel. This is 1. So these form arbitrary basis pairs. So we can always rewrite the state in terms of these new basis vectors. Okay, so let's do a little quiz. So previously, we saw that a way to parameterize general qubit state was according to this. So this is a slightly different way of writing this alpha beta, basically, but this time with angles. Okay, so according to what I've said before, so what would be the orthogonal vector to this guy? State that's orthogonal to 0b. Okay, so same. Okay, switch the positions. Switch the positions and minus 9 here. Anything else? Right. Yes. Yeah, exactly. Because according to what we had here, we got to switch them, complex conjugate, put a minus sign. Then it'll turn out to be orthogonal. Okay, then show that vectors are orthogonal. Might need a line of working. Sorry, the what? Yeah. And then what? What? We got it there. That's right. Yeah. I see that. We're writing it down. So basically, this one we've got to take the complex conjugate of this thing. Okay, this is just what we just wrote here. Then basically only the 0, 0 and the 1, 1 survive, right? 0 and 1, 1, 0, 0. So we're going to get this times that. Here the I sine 2 cos 2. And then this one times this one, but with a minus sign. So cos 0 over 2 sine 2 equals I 5. That's the same. 0. Okay, and then so we've got beta in terms of the alphas, right? Sorry. The b vectors in terms of the alpha, right? Here we've got again b vector in terms of this is in terms of Alice's vectors, right? How would we write the A vectors in terms of the B? So we want to invert that relation. I think this one definitely need to write something down. You need a pencil. Maybe you can use this. You can use the blackboard if you need. It's not very private, but you can you can use that. if you do it like this, it doesn't cancel. Like, I mean, you basically want to have only one thing on the right, right? But so in order to make like something like this cancel, you need some extra factors here. So for example, if you multiplied, sorry, I don't want to blind you with my laser, but if say you multiply this one with sine theta over 2, or e to the I sine theta over 2, right? And then if you multiply this one by cosine theta over 2, then you can engineer this thing to cancel out. Okay, well, let me show you. So, I think some of you are starting to get the have the right approach. So suppose we want to make this term cancel out on the right hand side, right? So basically the idea is we're gonna add these two equations together, but we need to multiply the equations by some coefficient so that these factors will cancel out. So what we're going to do is we're going to do something like 1 times by cosine over 2, equation 1, plus e to the I phi sine theta over 2 times equation 2, right? And so if we do that, then basically this term will be e to the I phi sine theta over 2 cos theta over 2, right? And this term will be e to the I phi sine theta over 2 cos theta over 2, but then with a minus sign. And then when you add the equations, this term will cancel out. So that's basically the strategy. 0b e to the I phi sine theta over 2. So this is the left-hand side. And over here, we also need to multiply by the same factors. So this one will be cosine squared theta over 2, 0 alpha. This one will be phi cosine theta over 2, sine theta over 2. And this one here is going to be this and this cancel out. This will be just sine squared. 0. And this one will be exactly the same factor. And then we've kind of engineered this to cancel out, right? And then what's even nice here is that, oh, sine squared plus cosine squared. So actually, and this is already the inverted relation, right? So it's 0a is equal to that stuff. Yep. 1, you can do something like that. What you should get, of course, is the state that's orthogonal to this. So the correct answer should be basically this thing swapped minus sign complex conjugate. That's what the answer should be. You can also prove it using just the algebra. Okay, right. Last slide of that one. Any questions? Nope. Okay, well, let's make a start on the next set. Oh, yeah. I think there are not really many equations to remember, actually. So the probability one, like the m times something.
Like, are we allowed to have like a cheat sheet?
Generally no. Generally no, but but to be honest, there's actually not that many formulas. Certainly, there are things like definitions. For example, this X, Y, Z matrices, like they'll come up again, like we did them before. Those things I give you, they're sort of definitions. But there's really not many formulas exactly. There's actually a few definitions, but there's really not much to remember. So, I would say that probably if you just do a few of the questions, you just probably remember the formula very quickly, and then beyond that you wouldn't really need it. But if you didn't practice it, you probably wouldn't know how to apply the formulas either. So, So no, there isn't, but I don't think it's like such a big shouldn't be a big issue for you. Okay, let me know if it is. Before the midterm. Okay, so this thing is kind of combining two concepts. So we did measurements, and then we also talked about how you can have different bases, right? You can represent states in different bases, and we can actually kind of combine these two ideas. And central to this will be our more generalized measurement device. So if you remember a couple of slides ago, we talked about measurement. We had this thing where some particle goes in here, gives some reading, tells you what the measurement outcome was. The new feature is this kind of knob here. And what we'll see is that basically a feature that you can measure in not just this 0-1 basis, but other bases too. So you can change the basis of the measurement. What we're going to talk about. Okay, so maybe we don't really need to recap, but because we just recapped already at the beginning of this lecture. But basically, measurements work like this, and the measurement that the only type of measurement that we were talking about up to this point is a measurement of 0 and 1. Right? So you might think that's it. That's what measurements are. But actually, there are other types of measurement. So you can actually, for measuring 0 and 1, the probability rule was this modulus squared. Or we could use measurement operators like this. And we could get the new state and the probability. So, so the point is that measurements don't just have to be done in this 0-1 basis, right? Because that's actually just one type of basis that we represent a state. Just like in the way that we can write the state in the 0-1 basis, but we can also write the state in some other basis. You don't have to write all the states in just 0 and 1. We can choose some other basis states. In the same way, we can actually do measurements in other bases, and we don't have to stick to the 0-1 basis. And so we just learned that a general, for a qubit, a general set of basis states, like we could write it as this. Change the notation a little bit. Call it, I can't remember why. I call it S0 and S1. This is some other orthogonal pair of states. 0-1 is our original one. It's our sort of most intuitive basis. S0, S1, and maybe it's another basis. So we can write the state like this. general state. In terms of S0, S1, coefficients A and B. These A and B states are coefficients are normalized. And basically what I'm saying now is that, so let's say we have a different measurement device. Previously our machine was something that measured in 0-1 basis. Now we've got a new machine, it measures in S0 and S1 basis. Okay? And basically how it works is exactly the same. So you have some state here, written in terms of S0, S1, stick it into the machine, and basically the probabilities of it being S0 or S1 are just the coefficient squared, A mod squared, coefficient of S1 is B mod squared, and the state that you get after that is S0. Now, S0, S1 are physically different states. They're not the same as the 0 and 1, right? But basically we've got a new machine, so it collapses to new states, and the probability rule is more or less the same. It's exactly the same. So I'll just have a little example. So for example, let's say you had this state, alpha, beta, in the 0-1 basis, right? And we've been saying, well, we can rewrite this state in a different basis. We can rewrite it in this plus-minus basis, right? And if we do that, then we'll have different coefficients, right? We just did that in the last lecture slides. So what this means is that if we have a machine, say, that instead of measuring in the 0-1 basis, actually measures in the plus or minus basis, then what this means is that actually it will go ahead and measure, after the measurement, because it's measuring in the plus-minus basis, it will measure that one. Right? So after it gets plus, it will become plus. After it gets minus, it will be that. Then the probabilities of these things will be a bit different, right? Because it won't be just alpha squared, beta squared like we had before. It's actually the modular squared of this thing in the plus-minus basis. And so the probabilities will be alpha plus beta mod squared of 2, or alpha minus beta mod squared. So you can kind of see that. So this is actually where the fact that the wave function is complex or has a phase actually makes a difference. So let's just maybe look at this example, and that'll be the last thing for today. But in the previous case, when we were just measuring in the 0-1 basis, right? If you get zero, the probability of this was alpha squared, and then the probability of this was 1. This was beta squared, right? And we were saying that actually this sign doesn't do anything in terms of this measurement, right? Because mod beta squared, okay, this could be plus, minus, would have an I here, wouldn't matter. Like, probabilities don't make any difference. So it looked like having complex numbers here is sort of a bit redundant, because after all, if you're gonna try to find out something about a quantum state, a measurement is the only way that you can get any information out of it. And then if the measurement is invariant to phases or signs or something, then why have it, right? So this is why actually you do need the phases and complex numbers and so forth. Because now, if with this same state, okay, so let's go back to minus, right? Now, let's say we're doing a measurement in the plus minus basis, right? Okay, let's start with just plus, so it's the same as what I've got on the slides. But the probability of this one will be alpha plus beta squared, which is according to what I've written there. Probability of this one will be alpha minus beta squared. Right? Now, if I start changing the signs here, then the probabilities of these things will change, right? Because okay, maybe I should have done a specific example. Let's do a specific example. So if this was 1 over root 2, 1 over root 2, probability of these ones will be both half, right? And it wouldn't matter that there's a phase here. Right? Okay, now if we're doing measurement in the plus minus basis, what I've got on the slides there says that this should be 1 over root 2 plus 1 over root 2 squared over 2. That's actually equal to 1. And this one will be 1 over root 2 minus 1 over root 2. So obviously that's 0, right? But of course, if I change this one to a minus sign, these are unchanged. But now these probabilities will flip, right? Because now this one will be minus and this one will be plus, right? Then all of a sudden this one will be probability 1 and this one will be 0, right? So this sign will make a difference for this plus minus basis measurement, but it doesn't make a difference for this 0, 1 basis measurement. So this is why actually this you do need these phases, because depending on the measurement that you make, it will make a difference to the outcome. Now, if you're wondering, okay, what about I? What if this was I? So in this case, actually, it wouldn't change the probabilities, because in this example, it would be plus I. This one would be minus I. And in this example, it would be both a half. But actually, there's another basis that you can measure in. So not just plus minus 0, 1. There's also another basis, which I call, using, I think I call it usually plus y and minus y. And for plus y, the basis states are defined like this. And like this. Okay. I won't go through it today, we don't have time, but what you'll see is that for this y plus or minus y basis, this is where this I now becomes important. Okay. So then it'll be a situation a lot like this, where it's like that will be like probability 1 for this one and 0 for this one, and then if you start changing the signs, it'll flip. Okay. All right. Any questions? Okay. Well, that's it for today, and see you next week.